And after the first lecture on quantum gravity, it's now the time to look at the philosophical side of quantum gravity with Nick Hugget from Chicago. So you have 1 hour and you have the stage.
So yeah, thank you. Thank you very much for having me. So as Francesca says, yes, I'm going to talk about the sort of what philosophers have made with quantum gravity so far. So I'm being interrupted.
Could you share the screen so like we only see the slides and not your Go again, stop sharing and start the sharing again.
Yeah. So, okay. So how do I get the meeting controls back?
That's the meeting.
Okay, excellent. Everyone good? Okay, thanks. So yeah, well, hi everybody, and hi to people on Zoom. So my brief was to talk about the philosophy of quantum gravity, or philosophy and quantum gravity. So what I'm going to do is give, in the hour that I have, an overview of sort of the main things that philosophers have talked about or thought about in quantum gravity. So my goal here, in an hour, I'm not going to be able to give any particularly sort of substantial lessons or make any really sort of deep points. What I had in mind, first of all, was that for these lectures, it would be really useful to, set things up to help philosophers and physicists talk to each other during the conference. So what you should sort of mainly, a main goal I had in sketching the sort of philosophical territory was to try to help physicists understand where philosophers might be coming from when they talk to them. So just try to set some background on the table so that you have a kind of sense of, what's motivating philosophers, what they found important, so that you can hopefully get conversations going more effectively. A sort of secondary goal in, again, sort of sketching the territory here is, I think clearly there are questions that haven't yet been addressed by philosophers that should be, And so if you sort of see the boundaries, hopefully in discussion we can push beyond those boundaries during the rest of the week. Okay, so things are going to be pretty sketchy. I'm going to talk in quite a general way about most things. There's one topic I'll talk about in a little more depth, but even then it'll be pretty quick. So please be tolerant of that in the cause of the goals that I have. If you want to ask questions while I'm speaking, that's okay. I may have more things to say here than I have time for, but I just wanted to make sure, I was ready to give you as much as possible. But yeah, ask questions and I'll either come back to it or I'll try and answer if I can. So, good. So one of the things that I definitely sort of want to do is just, while talking about some concrete issues, is also to reflect on, what the relationship between physics and philosophy is, and how I think philosophers can interact profitably for both sides with physicists. So a kind of example I like to talk about, first of all, is a historical one, which many, but maybe not all, will kind of be somewhat familiar with debates in the 17th century, in the birth of the scientific revolution and modern physics, about the nature, well, in the first place, it looks like, of the nature of space and time, debates between, in particular, Descartes, and then criticized by Newton, in turn criticized by Leibniz. I'm sure lots of people here are sort of familiar with sort of thoughts about relational accounts of space and mechanics that go back at least to this point. So there are some busts of the protagonists here. These debates, seem, unusually treated as such, as philosophical, and indeed they bring in all kinds of considerations that would seem very weird to, I think physics and indeed philosophy today, sort of religious considerations, big metaphysical principles. But what I want to say is you can't really understand what's going on in these debates, and really what's at the core of these debates between these three, sort of especially, is trying to understand what motion is, and in particular, what is the right notion of motion for the physics, the mechanics that was being developed at the time. Okay, so although they're giving philosophical arguments, at the center of what they're trying to do here is actually was really important for physics at the time, gets straight on the idea of what's the right concept of motion for physics. And indeed, if you read when you go and read these three carefully, the different things they're saying about the nature of motion, I would say, are tailored to the different kinds of mechanics that they're developing. I mean, they're all headed sort of in the same direction, but have different ideas about how to formulate mechanics. And those philosophical debates are at root an attempt to understand the physics that they're developing. Okay, you're probably also familiar with, in the early 20th century, and sort of Einstein and others thinking, Poincaré before Einstein, about the nature of space and time leading to relativity. Those also look like philosophical debates, but clearly in the service of developing physics. And similarly, the idea of in quantum mechanics, we have philosophical questions about the nature of cause, separability, and so on. Again, trying to work out the meaning of these concepts in physics. Those times, those periods, these kinds of questions lead physics into philosophical territory. And basically, what's going on here is, particularly at times where physics is revising its most basic concepts, the basic framework, what that does is open up questions of what's the right method to apply, what are the principles that are central to physics at this time, what is it to give an explanation, what even do the terms of the physics actually mean? When physics changes dramatically, then these questions get opened up. And those questions then really take us into philosophical territory. And that's where philosophers get interested, but also physicists do as well. Okay, so the new physics requires philosophical methods, philosophical approaches, as well as formal and empirical work. Okay. So looming over this, I haven't put his name over here, is Thomas Kuhn and the idea of a paradigm shift. I don't mean to buy into everything that seems to be suggested or taken to be suggested there, but I think the basic point that fundamental questions get opened up at times of seismic shifts in physics is right, and that philosophical work does come in at that point. So I take it, well, the premise of my talk, and I take it that's kind of the premise of a meeting to bring physicists and philosophers together, is that in quantum gravity, that's the kind of situation that we find ourselves in. And so that's what I want to kind of explore in the talk today. Okay, so this is I think 4 or 5 times I'm going to return to this question about the relationship between physics and philosophy. Hence the Roman numeral at the end of the subtitle here, or the slide title here. So I started with the question of what is motion. This question became very popular around the 1960s, 1970s, 80s in philosophy of physics. So I think it'll also be useful to kind of sketch to you sort of the starting point that most philosophers will have for thinking about philosophy of space and time, particularly in regards to this question about what is motion. So this work, comes out from people like John Ehrman and David Malamud, and I think it'll be a very familiar sort of picture to many of you, as they were very influenced by the work that was going on at the time in general relativity. But the stories, in a nutshell, and again, I'm being very brief here, is going to be, first we think in terms of differential geometry. The natural thing to do is distinguish the manifold from the geometry that lives in it. And then one reasons as follows, well, what geometry are we supposed to have? Well, look to the laws, look at the symmetries of the laws, and then pick the geometry which has the symmetries appropriate to the laws. If the laws have Lorentz symmetries, then you need a metric with Lorentzian symmetry as well. Okay, so that's the story. There's more philosophical disagreement at that point, whether you should think about the sort of symmetries coming first and determining the geometry, or whether you should think about the geometry being somehow given first and that determines the symmetries. I think those are probably more philosophical questions, or questions usually often of more direct relevance to philosophers, maybe than physicists. But the first, really the more traditional view is the idea that nature gives you a geometry and the laws conform to it. More recently, people have been, certainly a group of people have been interested in or defending the second kind of position, where you should think of the laws as more fundamental and the symmetries from there, and then the geometry is just, that's what we mean by geometry. Really, it's just whatever the symmetries of the laws are. That kind of view associated with Harvey Brown, for instance. But what we've done, what this philosophical move of distinguishing manifold from geometry has done is sort of broken things up into 2 questions. So the first part has to do with what the geometry is. And then there's a separate second set of questions that sort of focuses on the manifold and asks, well, what's really the significance of diffeomorphism symmetry? We think about the whole argument. Does that mean points exist or that points don't exist? And I suspect most people in the room take one side on that issue, but I think it's more controversial in philosophy about what one should actually conclude. Okay, so that's the basic sort of story. sorry, I put this as the question of what is motion. That's really built into slide 1. You know, which motions are absolute? Well, it depends on the geometry. Once I've settled the geometry, then I ask, you know, what motions are actually going to be absolute according to that. And sort of the key answer is if I have an affine geometry, then I'm going to be able to distinguish accelerations from non-accelerations. And so acceleration will be absolute, but velocity, for instance, will not. Okay, so again, that's a very kind of brief sort of 4-minute survey of what a lot of philosophy of physics in the last part of the 20th century and up till today looks like, the kind of basic framework. Lots of disagreements on particulars, but that's the kind of very general framework people have. Okay, so now I want to turn actually with, you know, I've got my historical example and I've sort of talked a bit about, you know, philosophy of physics, contemporary philosophy of physics. Now I actually want to turn to philosophy and quantum gravity in particular. I'm going to focus on the question of what people call space-time, I mean, people, including myself, you know, refer to as space-time emergence. For philosophers, that's a contentious use of that word, but I will go with that today. That's a question that I've been involved in quite a bit, so that's one reason I'm going to focus on it. But I also think this is a question that a lot of the literature, that's a sort of focus of a lot of the literature, or rather locus, I guess, that a lot of questions sort of focus around this question. So what people appeal to here quite often, and perhaps either positively or negatively, but another important idea that's in the philosophical air here is the idea of functionalism as a way of addressing the question of space-time emergence. So what I want to do is, well, explain the sense of emergence, explain the sense of functionalism. I think it's useful in its own right for people to sort of have in mind, but I think also as a useful kind of framework, again, thinking about how, or understanding how philosophers tend to think about these questions. All right, so the starting point here is the idea that, you know, one thing you do in physics, and I'm not making a universal claim about the nature of all physics, but an important thing is, you know, we want to explain the less fundamental parts of the world in terms of the more fundamental parts of the world. You know, often that takes the form of I want to explain what the big things are doing in terms of what smaller things are doing. So that's the kind of general thing that's going on here. So some examples of that, obvious things, like to explain the ideal gas law in terms of kinetic gases, thermodynamics in terms of statistical mechanics, classical mechanics, presumably in terms of quantum mechanics, Kepler's laws in terms of Newton's laws, Newton's in terms of general relativity. We also, coming to the topic of this, this meeting, we'd like to explain general relativity and quantum field theory in terms of quantum gravity. Most of my work is sort of thinking about string theory, so this is a picture I have of this. I have a string, and if it's vibrating in the right, if it's in the right state, then it corresponds to a massless spin 2 particle. And if I aggregate those, I can build up a a coherent state of gravitons, essentially, and then I can take the classical limit, and that's supposed to look like a classical metric. Okay, so there's a sort of the kind of story I have in mind of explaining, trying to explain GR in terms of something more fundamental, string theory in the case of this picture. And I'm going to put one other example up here, which is the mind in terms of the brain. I mean, psychology isn't a part of physics, but the story is going to be the same, and that tends to be a story that, you know, philosophers outside of philosophy of physics have focused on. So it's a kind of useful example, I think, also for sort of thinking about what's going on here. And there is a little point here for philosophers. People, including myself, take over the functionalist framework from philosophy of mind to quantum gravity. But I just want to point out one at least important difference, so that this is what the one philosophical point maybe that I'm going to make. Okay, so we're trying to explain the less fundamental in terms of the more fundamental. Sometimes that's perfectly straightforward, or at least it'll seem to us now. For instance, in the explanation of the ideal gas law in terms of the kinetic theory of the kinetic gas theory, the ideal gas law relates how thermometers and pressure gauges are related to one another, say for a fixed volume. And, makes sense. You do this in very elementary physics that, what's a pressure gauge doing? Well, it's just measuring the momentum transfer from the molecules that are colliding with it. And so there's a very natural story about why we would identify momentum transfer with pressure. Similar for temperature, if you think about the expansion of an old style thermometer. There's a very natural kind of story about why this is an adequate explanation. I would say sometimes that explanation is straightforward. So if we're trying to explain the ideal gas law in terms of kinetic gas theory, yeah, it's pretty clear why they're behaving in the way they do in atomic terms. Of course, there's something a bit anachronistic about my example because people didn't think the kinetic gas theory should be taken literally true for quite a while, but let's put that aside for now. But I would say more often the situation is not sort of straightforward like this. What happens more often is that although the less fundamental can be sort of formally derived from the more fundamental, there are complications that kick in. So I think the last trip back into history, the derivation of Kepler's laws from Newton's, and again, we're talking about the same period, and Newton, Descartes, and Leibniz are important players in this. It was very hard for many people to, accept that Newton's derivation of Kepler's laws in the Principia was really anything more than formal. The Cartesians accepted the derivation and accepted the formalism, but could not accept that this was real sort of physics that they were seeing being described here. Just because the very idea of action at a distance, well, to a Cartesian, I mean, it is actually self-contradictory if you really have the mechanical principle. Things have to hit each other to actually act on one another. But at the very least, there's a lot of talk about how action at a distance it can only be miraculous. And indeed, even Newton expresses skepticism about this as well. So maybe action at a distance is self-contradictory, or at very least, a lot of comments of a strong flavor that it just can't be admitted as a physical principle. This just can't be how explanations work. And yet, over time, people came to accept it. Of course, the field concept and the idea of locality flip things in some ways back the other way, but that's the sort of story here. But a lot of times, things are a lot more complicated, and the formal derivation does not immediately convince people that we have actually a proper explanation. Okay. Things are more extreme when the two levels, the less fundamental and the more fundamental, seem fundamentally different. And I think that's about as much as I actually want to say about the nature of emergence. I will, that's the general idea that we have one level being explained in terms of another level, in which the two levels seem deeply qualitatively different. That's kind of all I mean by emergence here. There's all these cases I'd be happy to talk of in emergence in that way, although my friends in philosophy of mind would be pretty angry about that. Okay, so examples of that. Well, taking the classical limit of quantum mechanics, well, there's lots of kind of controversial questions there about exactly the right way to do that. But, people are still, many people are still worried about the interpretation of quantum mechanics. I don't mean to take a stance on that now. I'm just making the observation that, many people still not disagree about what it is that quantum mechanics even says about the world. And so, it's, if you're in that position, how can you really be thinking, how can you be convinced that you've really explained the classical in terms of the quantum. If you're not even sure what it is, what complementarity even really means, say. So to introduce a little bit of vocabulary here that philosophers tend to use, and putting this in a somewhat linguistic term, but in a linguistic way. The problem is that the terms, just the very vocabulary of quantum mechanics, the things that quantum mechanics is talking about, seem to be troublesome. We don't properly have a grasp of them, it seems, so we use the word to say they're troublesome. But classical mechanics, okay, that seems okay. All right, there are interpretive kind of questions about classical mechanics as well. But in relatively speaking, classical mechanics, we seem to feel we understand what's going on there. And the question is, how to explain all that stuff in terms of quantum mechanics. Okay, so that's one example. Different example, I said I would come back, would use, which is the mind-brain example. There things are reversed, right? In the first example I gave you, the less fundamental classical mechanics, that seems okay, and it's the fundamental quantum mechanics that seems troublesome. In the mind-brain case, things are reversed. It's the less fundamental, the mind, that seems weird. I want to kind of understand the nature of the mind, and it's the more fundamental, the neurological, that seems perfectly normal. That seems like just a continuous part of physics. How we go the other way around. Okay, so we have this same sort of situation of troublesome and okay, but the levels are switched. And then we want to come to the explanation of general relativity and quantum field theory in terms of quantum gravity. Well, it depends on the flavor of quantum gravity that you're talking about, how radical a difference it makes to the world. But I want to sort of just think about very radical proposals in quantum gravity in which, in some way or other, the fundamental furniture of the world turns out not to be fully spatio-temporal. And I'll give some examples of how this goes, but in different ways, the world is not quite spatio-temporal. At the very least, maybe it's just discrete, but there are more radical situations that we can have instead. So I like, it depends on the flavor, but let's consider theories in which the fundamental furniture, and I quite like, Daniele talks about sort of atoms here. Okay, so imagine that there's something like non-spatio-temporal atoms. Somehow they're going to be combined. Don't think too literally about atoms. I'll put the scare quotes around it here, so you're not really thinking about atoms. I'm just using this as a nice kind of evocative word for whatever it is that the world is ultimately populated by according to quantum gravity. Well, look, if they're not spatio-temporal, they somehow don't live in space and time properly, then that's pretty troublesome. We really have to think about what that means, how we're supposed to understand them. So this is more like the same case as the quantum mechanics case, except maybe we're in a slightly worse position because people historically and really still, as my earlier slides indicated, sort of worry about the nature of the spatio-temporal, the less fundamental, the GR that we're trying to recover. What is space and time? Right? What does diffeomorphism invariance tell us about the manifold? All right, so there's something problematic about both levels here, although, again, the quantum gravity, more fundamental level, definitely more troublesome. Okay, so let's, the functionalist sort of response to this. So there's a picture here of David Lewis, who's, well, love him or loathe him, hero or villain of 20th century analytic philosophy, depending on what you think and what you take from his work. And actually we'll take sort of very different things. Suggested an approach to this, and I like to sort of sketch this out. So our first problem was, what are these things that we're sort of talking about? What are the troublesome terms refer to? What are those troublesome things in the theories? So, obviously, in Lewis's proposal, there's a lot of other things that he's trying to address, but focusing on that problem, well, what are we talking about? Look, if we have a theory of some entities, that they're non-spatiotemporal or whatever they are, we want to understand what we're talking about. Well, how are we going to, how do we describe what these things are? Well, the only thing we really have to hand is the theory describing them. So really the idea is if you sort of accept, or not even accept, just sort of contemplate a theory, as a possible story about the world, and you want to think, what does that involve? Well, part of it involves is thinking that the things it's describing are the things that have the properties that the theory says. The way we can define them is functionally, in terms of what it is the theory says that they do. It's the doing that's important here that gives us functionalism. So that's the basic idea, and I give it as a 4-step plan. So we start by thinking about what the fundamental terms do. Well, we can always define them in terms to be the things, they denote the things which ABC. So the theory says, there's these things that ABC, these things do A, these things do B, together they C. So the troublesome terms of the less fundamental theory, we don't know what they refer to already. Well, they tell us they refer to the things that do what the theory describes. We can do the same thing with the more fundamental terms. We don't know if we don't have an independent handle on what we're talking about. The things we're talking about are just the things that do what the theory says. Okay, so in a sense, I haven't made much sort of progress yet. I mean, I'm just, as I say, kind of making explicit what it is to even sort of contemplate a theory as a theory of the world. It says there are some things that do something or other. So that's what the terms of the theory means, denote. That's what those things are. They're the things that do this. Of course, the next step is to start to actually accept the theory and think not only, are these objects the things that do this, if anything does, but to actually believe the theory and think that there really are things that do that. What we want to do, the big step in the program is the 3rd step, is where we show, this is the explaining part, that the more fundamental objects, the things denoted by the terms in the more fundamental theory, in some way or other can do the same thing as the less fundamental things. Usually we have to sort of aggregate, we have to have a whole lot of atoms to get the ideal gas law, we have to have a whole lot of neurons to get psychological phenomena, okay, we have to aggregate statistical mechanically to get thermodynamics. But what we find is, look, those fundamental things, they don't just do this X, Y, Z that the fundamental theory says. If they work together well enough, they can also do ABC, which is what the less fundamental things do. So that's the place where you come to actually believe the theories, and more than that, you believe that the fundamental entities are doing the thing that we thought was that we also think is what the less fundamental do. And one point that Lewis wanted to sort of make here is, then in fact the job is done. If you've defined things the way 1 and 2 say, and you've come to accept that the less fundamental things are doing the more fundamental things are doing the less fundamental stuff, then it's just a logical theorem that they are the less fundamental stuff. Okay? Because the less fundamental things those are the only things that do ABC. And so if I've shown that the more fundamental things also do ABC, they just got to be the same thing. And that's just logic. So all the kind of empirical work, ultimately, 1 and 2 is really a definition. I mean, you've got to write down the theory. this isn't really a chronological story, but a logical story. 1 and 2 is just definition. 3 is where you actually come to believe things. You actually have to have evidence and arguments and reasons. But once you've done that, just logic, you're done. You've now kind of figured out what the less fundamental things are. Okay, let's apply that to our examples. So mind first. I'm just going to go through these points. Okay, all right, so same solution. We've got to understand the troublesome terms functionally. So thinking in terms of the mental. So what are the kind, what do sort of, what do mental terms refer to? Sort of pain sensitivity, we're thinking about sort of beliefs, desires. Well, it's an important part of psychology that what those things do is make you act in certain ways. That's kind of natural way to think. Not exhaustive, but that's a sort of important point. So you might think, and well, this is some sort of very amateurish folk psychology here, but you would tell a story along the lines of something like this. What is sort of sensitivity to pain? Well, it's that state which causes you to move your hand away from the flame and say, ow, if you get sort of too close, and, well, ... lots of other kinds of things. Right? So that's the sort of functional, that's, not even a sketch, a sort of general gesture in the direction of a functional definition of mental terms, but there's one of the things pain sensitivity does. Okay? Then we have to give a functional definition of neurological terms. And neurons are the things, well, they're composed, as I say, a cell body, an axon, dendrites, and they ... Okay? Sort of fill in the theory of neurons for here. So that's sort of defining the terms. And then we will show, this is where the work kind of happens, one then sets about showing that everything that you thought the mental things could do, say pain sensitivity could do, can also be done by neurons. And then we've done sort of work done, because pain sensitivity is the thing that does that. And I've shown that, one has shown that neurons do that. That's what pain sensitivity must be. Okay. So I gave that example in the hope that it's sort of fairly clear how the story is supposed to be working here, and then we'll move on to the quantum gravity case. It's always a risk when you give an analogous case that people will find that more confusing than the target case. And always, if that's the case, forget about the analogy and we'll just go to the target. But I was thinking this would be kind of useful. But we can tell the same sort of story for space-time, and this then would be how you would sort of think about it. So first of all, we define, the terms of the less fundamental theory. Think about what that's about. And so space-time, what is it that, we want to define space-time. What is it that space-time does? Well, various things you might sort of think there, and there's actually kind of debate and people working on this in the sort of philosophy literature. So, but space-time, well, it sort of provides inertial structure, sort of tells things how to move, provides geometry, there's going to be a metric. It also maybe we need to have a story about how the metric has chronogeometric significance, that it actually relates to space and time measurements. More primitively, we have space-time, so we can talk about location, and so the idea about sort of, say, point coincidence or something like that. That seems kind of a role that space-time plays. Other kinds of relations between locations. You can sort of think of different things that you expect space-time to do, what it actually does for you, what its role is supposed to be. Okay, then we have to define the non-space-time atoms. Well, here we get to sort of pick your favorite, your preferred approach to quantum gravity. Space-time atoms, well, maybe they form causal sets. Maybe they're whatever M theory will describe. Maybe they form spin networks. Maybe they're fields over a group. Maybe they're whatever makes up a non-commutative space, and so on and so forth. So pick your theory, and that'll tell you what the non-spatiotemporal atoms in the very general sense are. And then this is the part where we have to actually convince ourselves, because there's now showing. This shouldn't just be a formal matter. We have to come to believe that these things are actually doing the thing that we're talking about here. We need to show that whatever those atoms are, they can play the same roles as the spatio-temporal ones. If you get those atoms right, I will get inertial structure, I'll get a metric, I'll get location, I'll get other kinds of relations between locations, and so on. And yes.
Interrupt you, Nick.
No, please do. Yeah.
So how does understanding the function of troublesome terms provide a solution? I mean, I understand that you can understand what their function is, but you're saying that that's a solution to something. How does that provide a solution?
Good. Let me just go on to, let me finish this, and then, yeah. So, well, I'll just put the last thing up, and then I have the same sort of point. So, I'm going to go to the next slide, because I think this is going to, because I do want to kind of come to that. But that's, that's a very important question. So, I'll answer it in the mental case first, and then I'll do the sort of space-time case, because that was a sort of distinction I wanted to draw. So, in the case of the mind, this is sort of Lewis's idea. So we're not sure what the mental term, what these mental things really are. So the whole point of doing this functional definition and then doing this functional identification that I've just been describing is, okay, well, now I don't have to be worried about the mental terms anymore, or what those mental objects are, because really they're just this safe stuff. They are the neurons, and that's all good sort of physical stuff. Okay, so we can sort of talk about making safe the troublesome things in the less fundamental, because we have okay stuff that we can identify them with. Yeah? Okay. So I don't know how full an answer I'm going to sort of have for you, but I want to kind of point out that because things are different in the quantum gravity case, in the way that I said, that it's more complicated. Because remember, as I pointed out, in the mental case, we have the more troublesome at the, in the less fundamental, and we're going to explain them in terms of something that seems okay. In the space-time quantum gravity case, things are reversed. Let's just take the space-time stuff as sort of relatively okay, and what we're trying to do is feel better about the more fundamental, troublesome, non-spatio-temporal stuff in terms of what it's doing as in the way it sort of manifests itself as space-time. So, the way I was actually going to sort of focus on it here was more in sort of epistemic terms. In the mental case, but we can find out about the less fundamental stuff without having recourse to psychology. You can just do neuroscience and use microscopes and use chemical, physical techniques to understand how the brain is working. In the quantum gravity case, we don't have independent access to the more fundamental. In fact, the only way we have access to it is in terms of what it does at the spatio-temporal, less fundamental level. So, yeah. So ultimately, what one can actually get out of the functionalist program is, why should I not think that the non-spatio-temporal is troublesome anymore? Sort of the best we can do is, well, we're just going to have to accept that it does what the theory says. I accept the theory, so I've functionally defined, I know what it is sort of physically, But ultimately, the cash value of that is, in aggregate, it does the stuff that we see around us in space-time terms. So, yeah, that's kind of the answer to the question, which is, in a way, more raising another question, sort of more precisely than addressing it, that it's different from the mental. Good, good. Okay, one more thing I wanted to just sort of mention here in this is, you can also sort of see in the scheme that I've given up here, yeah.
So I just had this sort of question about the logical relationship between the less fundamental and the more fundamental, which is that I think the goal here is to show that that which X, Y, Z's also ABCs, but not conversely, right? Like you're not assuming the converse. It's not the case that if you ABC, then you're also going to X, Y, Z. Because if the definition is a functional definition, then it has to go through the fact that because you can X, Y, Z, you can also ABC.
Yeah.
So there's a sense in which there's still a gap between the less fundamental and the more fundamental. Like the more fundamental, more fundamental description is not forced upon you by the less fundamental one. It's one candidate kind of for.
Yes.
Right. Like so they're not identical, because I was a bit confused with the conflation of the two, because it seemed like the difference was not really fundamental between the less.
So I didn't emphasize this, but in the slide, there's the word sort of in aggregate, sort of inserted there. So of course, sort of, individual neurons, say, aren't, pain sensitivity, but what you're saying is that there are states of the neurons which are the states of pain sensitivity. Or, so, if you want to think about it in that sort of compositional way, if I put them together right and sort of aggregate in the right way, it's actually that's the higher level individual. But yeah. Good. Yeah. Thank you. So just sort of an analytic point. There's sort of two ways in which you might in which different approaches to quantum gravity might differ with respect to a sort of functionalist scheme. They might postulate, and this is the more obvious one, they may postulate different fundamental levels, so different atoms, but they also might have different understandings of what it is that you're trying to recover in space-time. Okay? So at the higher level, you might focus or emphasize different roles for space-time. So for instance, here I'm thinking about sort of approaches where you might try to recover the metric right away versus approaches where you might sort of try to operationalize the metric in some way and recover some operational outcome. So sort of scattering amplitudes or something like that. Okay, so second point, it's time coming to the relationship between physics and philosophy. So first of all, I think this sort of philosophy is sort of useful here because I think there's a nice sort of abstract scheme that I think may be useful for sort of conceptualizing what it is the task of quantum gravity sort of is here. I mean, I think a lot of people who are working in the field would generally sort of understand this intuitively, but sometimes it's useful to have an sort of explicit formulation. This analysis, though, also kind of points to where I think the philosophy comes up in the search for a theory of quantum gravity, in as much as it comes up in the sort of third step of the plan, which is the showing part. Okay? The part where you have to sort of show, i.e. convince yourself, convince other people, have grounds for believing that indeed the fundamental, it's sort of in aggregate, to sort of, is actually indeed playing the role of the less fundamental. But I don't, all right, so there's formal work to do there. Some formal derivation needs to be done. There's empirical work to be done there because one will then want to test novel predictions to have faith in the theory that it could be doing it. But there's also going to be there is going to be conceptual work here. We understand explanations in terms of processes in space and time. I've already kind of given you indications about how that can change, whether or not action at a distance, say, is admissible, even when we have space and time. But it's absolutely clear that if I'm trying to construct something from a physics that's non-spatiotemporal, we're going to have to rethink what it is to give a decent explanation, what principles can really be assumed, what's okay and what's not okay. And one can expect controversies of the same kind that Newton, Descartes, and Leibniz are comparable to their controversies. Okay? So that showing is not just going to be a matter of math, formulate some mathematics, make a formal prediction and test it. There's going to have to be a sort of conceptual shift as well about how to do the physics in these terms. And of course, that naturally happens, but that's naturally sort of requires philosophical thought and argument, I would say. Okay, sorry, that's the thing I was just saying. So we can't, again, if we don't have spatio-temporal explanations, when is an explanation explanatory? Just going to mention this sort of this is a bit of an aside, but people have kind of talked about this. One question here where this is coming up, I think, about what counts as a reasonable explanation in quantum gravity is to where, in what range, if any, can we really appeal to sort of gravity as an effective field theory? I mean, this is a sort of well understood sort of formal framework, but will all theories of quantum gravity, will the right theory of quantum gravity lead through the effective field approach to gravity? And in what regime could it actually be trusted? Okay. All right. So I reckon I'm going to be even more sketchy than I have been so far. And as I said, if people have questions, I'm happy for them to jump in. A lot more, what I have now is a bit of a laundry list of things that philosophers have been talking about. So I thought I would kind of run through these. Philosophy, outside of value theory, ethics, and aesthetics, tends to divide things up in between what there is, metaphysics, and how we come to know about it, epistemology. So I'm going to divide things up that way also. I see a question back there.
Degrees of independence, because it seems to me that it's conceivable, entirely conceivable, that the fundamental structure that might tell us about gravity or other things is so deeply buried that we can't get it, because I consider emergence, and I might wrongly consider it, to mean that we're trying to reproduce something that we know about, and that, so we mess around with the theory down here. But if we have to go deeper and deeper to the point that we can't possibly get it from what we know up here, then the only answer that seems to make sense would be we have to take something down, because we have our real perceptions and stuff, and in some way we need to bring those with us to even evaluate anything. But that leaves the answer then buried at the philosophical level. That means that if you can't, and I don't consider that emergence, and I'm wondering if you do, and if you think that that might be where the answers lie, and if that will be approached in any kind of a serious manner.
So, is your question about, something along the lines of, look, it would be sort of hopeless to try to formulate a fundamental theory that kind of threw away everything that we have now, so we have to make some decisions about what we want kind of reflected? Something along those lines?
Or not what we want to have reflected, because that's a result, but we have to bring something down with us to evaluate, to build on. I mean, we can't just build without having some understanding. We don't know for sure that the basic fundamental foundational thing would even be understandable. But do you think that philosophers don't seem to be going that direction? They seem to be trying to do what I think is an emergence kind of thing, that they try to reproduce something that exists, and they do marvelous things. I'm not questioning that, but what they don't do is they don't go down to the lowest level. There may be some who do, but it's not a general trend. The general trend seems to be to try to explain things, but perhaps we need to go down and try to understand nature.
So I think if I'm getting understanding what you're suggesting, and it's that, you know, philosophy first might give us good, you know, might tell us how we should proceed.
Exactly.
So to be honest, I'm more skeptical of that kind of role for philosophy. I think you're exactly right at picking up the right thing. You know, it's clear. I know people who approach quantum gravity obviously take different lessons about what it is they think really needs to be sort of built in at a more fundamental level, and people disagree about that. But I am really skeptical that, you know, pure philosophical sort of a priori argument could really give you any very useful advice there. I mean, sorry, I keep getting kind of hollow in my eyes. You know, in my eyesight when I'm looking at you, because I know, you know, he's given them, you know, good arguments for why we should have this or that built in fundamentally. And I think, you know, by reflecting on, you know, what current physics looks like and thinking about the different things that seem really central to it, one can get different ideas about what to build in. But I don't think any more than that can be done. Ultimately, it's going to be a matter of building the theory and, you know, seeing how it goes. So, yeah.
Thank you. That's exactly what I wanted to know. Thank you.
So, yeah. Sometimes people, you know, I do get that, you know, you hear that attitude. Oh, the philosophers should tell us what to do, but I don't think that's not going to work. Yeah. Much better at telling you what you just did do, something like that, I would say. Okay. Good. Metaphysical questions. So kind of quickly, Geometrogenesis, I wanted to mention. Daniele Aritti has done nice work on this, and people are starting to get interested in this, I think, important question. You know, if the atoms, I mean, I've done a little bit myself, if atoms are truly non-spatio-temporal, with an emphasis on temporal here, a reasonable question is, you know, well, do they combine into both spatio-temporal and non-spatio-temporal phases? You know, just as, you know, water molecules, you know, can have wet water and ice phases. But then can we also have phase transitions, and how are we supposed to make even sense of that? A transition is a change, but a change implies time. It's different at different times. So what are you supposed to do if it's time itself that's being born? People have looked at the question of, you know, what is a law of nature without time? In some sense, you know, one can think about laws without any real difficulty that don't have t sort of appearing in them or any sort of time. I mean, I already gave you the ideal gas law. But the question is, how are you supposed to get dynamics out of a theory that without time? So that's one sort of question, metaphysical question. Another kind of question philosophers have thought about, which is what makes a world, I will put this way. And the question is, you know, when you accept a theory, the things that I was talking about before, and you think they exist, you know, we are going into more philosophical, you know, pure philosophical territory here. Is what kind of does existence sort of amount to? And there's a very nice dictum from Aristotle that to be is to be somewhere, which emphasizes the spatial nature of being. So if we think in sort of relational terms, you know, well, to be is to be in relation with the other things that exist. And so a theory that philosophers, or view that philosophers talk about is the idea about, you know, what is a world, a universe? It's a collection, you know, what kind of collection of things is it? Well, it's a collection of things that are spatio-temporally related to one another in some way. And then, of course, we have the question, the world is a collection of things that stand in space-time relations. What is a world if there aren't any space-time relations? And some philosophers have kind of played with this. Michael Esfeld has sort of thought about this and just says, look, if there aren't space-time relations, then there really aren't worlds. He has a program where he wants to argue that this would make physics sort of borderline incoherent. One would need a very strong story about how this could be done. This is an argument he gives, a sort of skepticism that any theory of quantum gravity really could be non-spatio-temporal. So that's one kind of reaction people have to sort of the emergence functionalist story, is you're really not going to need it. My collaborator, Christian Wutrik, has thought about this in relation to the theory of possible worlds, which is a theory for modal logic for understanding necessity and possibility. It's again commonly thought that the different possible worlds are worlds of things that are spatially related to one another. So if there are no spatial relations, that sort of logic breaks down. And of course, then the question, if you're worried about this, the question comes up of what is some other relation do this? And I know I'm nearly out of time, but that's sort of okay. I wanted to mention this because there's some very recent work in the last year or two, which is very recent for philosophy, which I thought would be worth mentioning here, where people are starting to think about entanglement as a different way of making worlds in this sense. So I'm actually not even sure if it's come out yet. There's a paper by Rasmus Jackson, which uses the Ryo Takayanagi formula. I've never had to say that in public before, so I hope I did that okay. Looks at things like that formula and ER equals EPR conjecture. The natural thing to do that he's sort of playing with is, look, if we didn't have spatio-temporal relations, maybe it's entanglement that's the right way to sort of what makes a world. And so we change Aristotle's dictum. It's not, to be is to be spatio-temporally related. It's to be sort of entangled. And another paper by Cintian Sanchioni, applying to another philosophical idea, the Humean mosaic that some might have heard of. And of course, they often cite the Chow Carroll and Michalakis work on entanglement related to the metric. Just going to, so very quickly. So indeed, some of these questions that I've just been raising seem much more internal to philosophy. So certainly there are questions, certainly part of the relationship between physics and philosophy is not philosophy within physics, it's philosophy responding to discoveries in physics and thought in physics. So some of these things sort of go here, go under this heading, just a question of what philosophical doctrines need to be revised. But not everything in the metaphysics is of that kind. But certainly, if things get radical enough, and if we start answering yes to the question that I put up, then we may have to think about geometrogenesis and understand how that could be possible. People have sort of thought about that. It was a little quick, I'm afraid, but the background of what I was talking about possible worlds, as I said, that is for understanding, talk about what's possible and what's necessary and what would happen, about subjunctives, counterfactuals. And so that one reason, I hope, that philosophers are actually sort of interested in this stuff, and so the question, where the question of what is a world comes from, is because thinking about possibility, necessity, what if situations, what if things have been different in various ways, is an important part of physics practice. And so we do need a kind of handle on what's actually being meant when people are thinking in that way. So that's also a more positive connection between philosophy and physics here. Okay. I'm going to skip. I have slides on epistemology, and I will just go through those without sort of reflecting on them. People have been thinking about questions about how we can learn about quantum gravity and the problems for that. Those are important questions. Some of you were probably at a meeting in Munich a few years ago about what makes a theory, where this was sort of thrashed out, in particular about the notion of non-empirical confirmation, for instance. So that was a meeting of for physicists and philosophers. So that's clearly a question of the intersection. Really, one more slide. I hope you'll kind of indulge me with an extra couple of minutes. Because this is, I think, the sort of real topic of the conference. And I just wanted to say just give you some little bit of a sense of where philosophers are thinking about the role of information in quantum gravity. And it's going to be fairly quick because I would say substantially philosophers haven't really thought about specifically the question of what role information plays in quantum gravity very much yet. I gave you a couple of examples a minute ago about how people have started to think about what entanglement, how entanglement might play a role. So there are certainly exceptions to this. There's one very big exception. There's quite a philosophical philosophy of physics literature on the question of black hole information loss. That's definitely one way that people have got into this. They have also investigated at length in various ways how the mathematical structure of quantum mechanics fits with the structure of classical space-time. Sort of vast literature on the meaning of the Bell inequalities, for instance. More interesting work, well, not that's interesting, but sort of recent different work. Richard Healy's over here. I think he'll probably talk about some of the work he's been doing to think about things like GHZ experiments and how that it relates to the classical structure of space-time. So certainly that kind of work is going on. I haven't kind of quite included that under quantum gravity because I think of that as something like quantized GR maybe. Certainly those kinds of questions have been talked about. But really with that, I'm going to I will be turning things over to Wayne. Certainly philosophers have thought about quantum information theory, and I take it that'll be the subject of the lecture this afternoon. So, people have thought about quantum gravity, certain important things about information theory, but what I'm really hoping myself to learn here is to start to think more about the philosophical issues that come up when you put these things together. I think, that's kind of my goal for the conference. With that, that's me done.
Thank you, Nick. This was great and super useful. I have a question. You spent some time on this functionalist program. And for me, it was wonderful because I always heard about it, but never had a clear, and you connected it to the quantum gravity questions. And I found it very clear and very, very nice. So I have a reaction to that. Double. The first reaction was, yes, wonderful. That's exactly a good way of thinking. If I connect your lecture with the previous one by Hal, one could listen to Hal talking about this small tetrahedra, this quantum space, and then ask what you talk about, what this has to do with space and time, as we use space and time, say in general relativity or in general. And you give an answer here. It's a very good, very clear, and very clean answer. So yeah, that's a way of thinking about that, because it sort of takes away the heavy baggage attached to the word space and time in non-quantum gravity physics. Give a way of thinking about it and connect it. Oh, that's fantastic. But there's and that's where we'll come. The way you resolve it, it's in the functionalist terms in terms of what they do. Okay. But at the end of the day, is do. You never said what it means to do something. It's a sort of you gave just an example about pain. What you do is you say make us say wow, but that's a very simple example. I'm not sure it's sort of behavioral. Mm-hmm. What in by A, B, C, and then X, Y, Z, you refer to terms or more to terms? If they terms, like space, time. How do I interpret they do? I need an external framework in terms of which I understand what it means for a term or a piece of something of the theory to do something. So I have to put this into an empiricist thing. I mean, it allows us to do predictions, allows us to conceptualize the world, allow us, especially because you attach this very much to David Lewis. You put a picture of him. But if I think of David Lewis, I think a Humean mosaic, which just doesn't make any sense in quantum gravity, just by line one. I think of natural properties, which I'm not sure I understand in quantum gravity terms. So what does it mean to do something in here?
Good. So I'll tell you what Lewis means sort of quickly, because I think that it's probably, there is a sort of clean answer, but it's probably not a sort of super helpful one. I mean, he's imagining you have the theory you have your sort of theory written down in sentences, and literally what it is to do is to be the things that do the things that are described by those by those theory postulates. And there's nothing more than that, but this is because he frames things basically as a sort of semantic problem about defining what these terms are, and what he's worried about is, do these words literally refer to anything? And so you want to be convinced that there's only one thing that does what the theory, that does the thing the theory says about it. So does there means, satisfies, makes true this theory postulate. So that's kind of a nice sort of logical framework, but I think the question, then you're asking is, how do we actually apply that sort of in science? Because things are usually much more messy, and that's like a real idealization. Yeah, I mean, I think it is it's a harder question. I'm not convinced that there has to be a sort of general theory about what sort of doing kind of is, but one has to sort of pin down what is the, well, I don't know, the function, the doing, what is the thing that I want to be done, and I can kind of identify that maybe in the theory. I want to be able to talk about places where, I want to talk about events, sort of locations where things happen, and I want to see where they're coming from in the theory. So the doing in that case might be, I want somewhere where a scattering experiment can happen, or I can have a point coincidence, right? Two rays might kind of cross or something like that.
The role that they have when I use the theory for whatever I use the theory for, like prediction, understanding experiment, describing reality, everything that I do with the theory.
Yeah.
Is that it?
Yeah.
Okay, thanks. Thank you.
But I mean, I take it ultimately, you also kind of made sort of empirical meaning as well. I mean, ultimately, this has all got to have cash value in terms of what's happening in experiments. I kind of, there's going to be a scattering experiment for it. And I need to be able to describe that. So sort of for Lewis, that's sort of the empirical part is built in because there's going to be some words in the theory whose empirical meaning you already have. I tend to think more in sort of operational terms, that I kind of want to know, I have some particular experiment or phenomenon that's occurring, and I want to know I have a description of that, and I want to know how to recover all the parts of that phenomenon.
I have to close the discussion here. We can continue the discussion during the lunch and in front of posters, because it's really time to eat. Thank you so much, Nick, for the marvelous lecture.
Thank you.
Before you move to the buffet, I would recommend to go to the buffet with the mask, and please bring to the tables the food, and you can remove the mask once you are sitting. if you need, again, if you need internet connection, it takes just 1 minute to fill the form here, and you will be immediately online.